Bohr-Sommerfeld atom model. So this is a Bohr-Sommerfeld atomic model. So we call Bohr's as well as the Sommerfeld atomic model. So to overcome those, in the case of what we call Bohr's atomic model as well as the Sommerfeld's atomic model, the new model has been introduced, which we call it as a vector model. So what are the things which we have drawbacks in the case of the Bohr's atomic model and as well as in the case of the Sommerfeld model, we'll see. Then we'll move to the concept of vector atom model. So actually, the drawbacks which we have in the case of these two models is in the case of the first drawback, if you see in the original Bohr's theory, it was incapable of explaining the fine structure of the spectral lines even in the simplest hydrogen atom. So the Bohr's atomic model is failed to explain the fine structure of the what we call the hydrogen atom. So that is why Bohr's atomic model have one drawback here. And also, if you see in the case second drawback which we have in the case of the Bohr's atomic model is Bohr's theory is failed to calculate the energy of the system and frequencies of radiation emitted. So that is one drawback also we have in the case of the Bohr's atomic model. And if you go next drawback which we have is Sommerfeld modification through a theoretical background of the splitting of individual spectral lines of hydrogen, but it still could not explain otherwise, it could not predict the correct number of observed fine structure of these lines. Okay, so even what we call this Sommerfeld atomic model also didn't explain the fine structure of the what we call atom in the Sommerfeld also. So that is one drawback we have. So that is fine structure is nothing but the splitting of individual spectral lines of the hydrogen atom if you take. Okay, that is also drawback we have. And both these models like Bohr's atomic model and as well as the Bohr's atomic model and as well as this Sommerfeld atomic model, they didn't explain about the what we call a distribution of the electrons in the case of the atoms. Okay, how the electrons has been distributed, all those things does not explained by this what we call Bohr's atomic model as well as the Sommerfeld model. So that is also one of the drawback which we have. Next, if you go these both models, so they do not throw any light on the intensity of the spectral lines. So the spectral lines, whatever we have got, so they didn't given any information about the intensities of the spectral lines. So that is also drawbacks which we have in the case of the Bohr's as well as the Sommerfeld's atomic model. And if you see one more drawback which we have is these two models, like Bohr's atomic model as well as the Sommerfeld model, they didn't explain about the anomalous Zeeman effect as well as the Stark effect. So that are also drawback which we have. So whatever may be the drawbacks, whichever we have in the case of this what we call a Bohr's atomic model as well as the Sommerfeld atomic model. So these drawbacks can be explained by the vector atom model. Otherwise, to overcome the drawbacks whichever we have, this vector atom model, new atomic model has been introduced here. Okay, so the main contributions are for this is a Bohr, someone as well as a Gauss, Stern, and Gerlach. All these scientists are what we call contribution for this vector atom model. So what is the vector atom model? What is the concept of vector atom model? We'll see here. So first we'll go for vector atom model here. So we are studying about vector atom model. vector atom model. Vector atom model. So in the case of the vector atom model, mainly we have the two concepts. It as a quantization direction. Otherwise, we calling it as what we call spatial quantization. So some issue with the net we have. So now we'll see the vector atom model. Here concept of vector atom model. Just so as I told that the concept of vector atom model, it is there are two concepts which characterize the vector atom model, and it will differentiate from other models. So the as I told that the first concept which we have is a spatial quantization we have, and the second concept which we have is spinning of the electron. So these are the two concepts which we have uh, in the case of the what we call a vector atom model. So first we will discuss about the space quantization or spatial quantization, whichever we have. So if you discuss about the space quantization, so here according to Bohr's theory, the electron moves in circular orbits since the radius of the orbit remains fixed here. Right. Right. So in the case of the space quantization, I'm writing here space quantization, or we can call it as a spatial quantization, both are same here. So in the case of the space quantization, right. So in the case of the space quantization, as I told that according to the Bohr theory, the electron moves in circular orbit. Since the radius of the orbital remains fixed here, in the case of the Bohr's atomic model, as we studied the circular orbit, the radius will be fixed everywhere. So as the radius is fixed, hence the direction has only 1 degree of freedom in the case of the Bohr's atomic model. And in case of elliptical orbit concept, which has been introduced by Sommerfeld. Sommerfeld says that the electron is revolving around the nucleus, not in a circular orbit, but he says that the electron is revolving in elliptical orbits. So according to this Sommerfeld, otherwise in case of the Sommerfeld elliptical orbits, the electron is possessing 2 degrees of freedom. Okay, electron is possessing 2 degrees of freedom. So if you study about like according to Bohr's theory, it is having 1 degree of freedom. So 1 degree of freedom in the case of what we call Bohr's atomic model. So it is 1 degree of freedom we have, right? So 1 degree of freedom. And in the case of the Sommerfeld atomic model, it is having the 2 degrees of freedom. So two quantum numbers, one corresponding to the radius vector and which we have seen corresponding to the radius vector, the quantum number we called it as a nr, and the other corresponding to the angle, so which we call it as a n phi. We have been called it as a n phi. So two quantum numbers are sufficient to describe the electron in orbit according to the Sommerfeld. But in general, the motion of electron in an atom is actually three-dimensional. Okay, actually, in general, the electron is revolving around the nucleus. So if you want to explain the motion of the electron, it should be three-dimensional wise. We have to explain. Okay, so in general, the motion of electron is in atom is three-dimensional, and therefore it is possessing what we call 3 degrees of freedom. It is going to be have. So hence, in additional to the quantum numbers, whichever we have seen like nr and n phi, we have one more quantum number. We have to be one more quantum number to describe the actual state of electron which is revolving around the nucleus. Okay, so according to the Bohr's theory, we have only 1 degree of freedom, as we said that the electron is revolving around the nucleus in circular orbits. So only 1 degrees of freedom is required in order to explain the what we call about the electron. And in the case of the Sommerfeld atomic model, as it is revolving around the nucleus in the elliptical orbit, so we require the 2 degrees of freedom to explain about the electron. So we have like nr and n phi, two quantum numbers. So nr is nothing but which is a radius vector, and similarly, and n phi is nothing but corresponding to the angle we have. So actually, in general, as we said that in order to explain the about the electron in an atom, we required a three-dimensional thing we required. So therefore, it possesses a 3 degrees of freedom. So to explain the motion of electron in an atom, we require three-dimensional, and therefore it is going to be possess 3 degrees of freedom. It is going to be possessed. So hence we required one more additional quantum number is required to describe the actual state and of electron. Okay, so that is what we require, 3 degrees of freedom, right? So if you take the what we call classical mechanics, according to the classical mechanics, when when an electron moves in three-dimensional orbit, it may have all orientation with respect to the fixed axis. Okay, it may be having the all orientation with respect to the fixed axis. In this vector atom model, which is based on quantum theory. Okay, so vector atom model, which is based on quantum theory, not on the classical theory which we have. Okay, vector atom model is based upon the quantum theory. We have to explain the what we call about the electron in an atom. So it is going to be take the what we call quantum theory. So the orbits are assumed to be quantized in magnitude and direction. The what we call here the orbits are assumed to be quantized in magnitude and direction both. So in this way, the third condition quantizes the orientation of elliptical orbit in three dimensions and does not alter the original Sommerfield's orbits. Means whatever may be the concept which has been given by the Sommerfield, that is not going to be altered. So by taking that concept, that is nothing but the elliptical orbit concept, here we will be explaining about one more extra quantum number here. Okay, so the introduction of that what we call space quantization or a spatial quantization makes the orbit vector quantized. Makes the orbit vector quantized. So for this purpose, for the purpose of what we call a space quantization, we need a certain preferred direction with respect to what we call which the orbit may receive their orientation. Okay. Such a direction may be received by an external field of force, but that may be deform the elliptical orbits. Okay, to avoid this situation, we choose the external field is very small so that it does not deforms. That means it does not changes the orbital shape. Okay, so for easiness, the direction of the field is taken along the z direction. Along the z direction, it is going to be taken. The angle between the field direction and the direction which is perpendicular to the plane of the orbit is taken as a theta here. So according to this rule, space quantization, uh, according to this rule of space quantization, the electron orbit can only set itself in certain discrete positions. Discrete position means in different positions with respect to the field direction, and not in all positions, all possible angles with the field direction, which is suggested by the classical theory. So according to the classical theory, it should be continuous, whereas in the case of the quantum theory, it is going to be take only particular values. So basing upon that one, this space quantization has been explained. So which is this is known as what we call space quantization, and it was proposed by Sommerfeld itself only. So as I told that this vector atom model is having the contribution of all the scientists like Sommerfeld, Bohr, as well as the what we call Stengelack and Pauli, Goudsmit, all these scientists we have. Okay, so this is about the space quantization concept we have. And uh, next one that we have is next concept which we have is what we call a spinning electron, which we call it as a spinning electron. So this is one more concept which we have in the case of the vector atom model, right? Spinning electron. So in the spectra, like whatever may be spectra, if you take like alkali spectra, if you take, we observe that many lines consisting of a group of lines. So that means each single lines, if you see this is one line, but actually this is consisting of different lines, which are like so many lines like this. It is going to have. It has been split into different lines here. So a group of close lines you are going to be have. So to explain the multiple characters of the spectral line, so it has been given a new concept which we call it as a spinning of electron or electron spin we are going to be called here. So according to this hypothesis, that is spinning of electron, actually, the electron revolves not only in an orbit around the nucleus, but also it is going to be revolve about its own axis. So that is what new concept it has been given. So generally, we will think that so if you have a what we call a center where we have a nucleus here. So this is the nucleus which is positively charged, and we will be seeing that around that electron is revolving in the what we call in the elliptical orbits. Okay, in the elliptical orbits like this, it is going to be revolve here. So the electron is revolving. Say this in this direction, it is revolving. Electron is revolving in this direction. So uh, this is what we call it as a orbital motion of electron we are going to be called. Okay, orbital motion of the electron we are going to be called. So here, whenever the electron is revolving around this nucleus, as we says that the electron is revolving around the nucleus, and at the same time, this electron is going to be revolve on its own axis, revolve on its own axis. So like this, if we have an electron, so it is going to be revolve on its own axis. So again, the electron will be revolving around on its own axis. There are two possibilities to revolve this electron on its own axis. One is in the anti-clockwise direction. In this direction, it may be revolved. So this is one we have. And also, if you take this is the nucleus, okay, this is the nucleus if you take. So around this, it is going to be revolved in this elliptical orbits. In the elliptical orbit, it is going to revolve. So this is it is revolving on its own axis in the anti-clock direction. Anti-clock direction. Similarly, this electron, if you take, so there is a possibility that the electron may be revolved around the nucleus and as well as on its own axis in the clockwise direction also. In this direction also, you are going to be revolved here. So generally, the direction will be not in this direction. So it should be in the opposite. Here we should have, I'll draw that one. So here if we take, so here the electron, so the electron here, so actually it should be revolved in the opposite directions like this. It should have. Okay. So here again, take. So here in this direction, it is going to be revolved in the clockwise direction. This is a clockwise direction. So that means the electron here, it is revolving around the nucleus, and at the same time, it is revolving on its own axis. In both the cases, one is clockwise direction. In another case, it is going to be revolving in anti-clockwise direction. Okay. So according to this quantum theory, this spin motion, like a orbital motion, should be quantized here. So hence, a new quantum number, which is known as a spin quantum number, is introduced. It is going to, they have introduced a new quantum number, which we call it as a spin quantum number. So the orbital and spin motions are quantized not only in magnitude, but also in a direction according to the concept of this, what we call spatial quantization. So the two are considered as a quantized vectors, and hence the atom model is known as a vector atom model we are going to recall here. So here, as I told that again, when that is revolving body about an axis gives rise to some what we call mechanical angular momentum. Okay, whenever it is revolving around this, it is going to be gives rise mechanical angular momentum. If the body is charged, it gives rise to circular current and hence to a magnetic movement. Okay, so now the electron will be have two magnetic movements. Electron will be having two magnetic movement. One is due to the orbital motion, and the other is due to the spin motion. So the magnetic movement of the magnetic movement of the atom will be the resultant of two magnetic momenta which are quantized vectors. Okay. So similarly, the electron will now be with two angular momenta, one due to the orbital motion and another due to the spin motion. Orbital motion means it is revolving in this orbit. So due to this motion, it is having one what we call one orbital motion we are going to be called, and another one as it is revolving around this one, whether it may be clockwise direction or anti-clockwise direction, we have a spin motion we are going to be have. Okay, so the two fundamental postulates of vector atom model is one is a space quantization, and another one is what we call a spin quantization. So these two fundamental postulates of this vector atom model have been experimentally verified by the what we call experiment by the scientist Sten Gerlach. So which we call it as a Sten Gerlach experiment. We are going to be called. So this Stern and Gerlach, while studying the behavior of atoms in non-homogeneous magnetic fields, they have observed this what we call the concept whichever it has been given by this vector atom model. So this is what two new concepts like a space quantization and as well as the spinning of an electron. These two concept has been led to what we call concept of a vector atom model. It has been given. Okay, so now we will see about what we call orbital angular momentum and all those things. So here we have I'll share one more thing. So I'll share the So this is what we have a spatial quantization and as well as spinning of electron. Next, we'll move to the concept of this what we call different quantum numbers here. So first we'll move to the principal quantum number. So what actually the principal quantum number will have. So first, the quantum numbers which are associated with the what we call vector atom model are like a principal quantum number. So principal quantum number actually it is represented with n. We can represent here. So we can represent with n here. So this is the n which we can represent here. So this quantum number belongs to the principal orbit, yeah, to which the electron belongs, and it's identical that used in case of what we call Bohr-Sommerfeld theory here. So already we have seen that in the case of the principal quantum number, the energy is given by like a En, which we have like a minus 13.6 by n square electron volts. That is what we have seen. And here n value is nothing but it is going to be have what we call starting from n is equals to 1, 2, 3, and 4, and so on. We are going to be have. Okay. So the total quantum number n can have only non-zero positive integral values. N is equals to 1, 2, 3, 4, and so on up to infinite we may be having. And if n is equals to 1, we will be calling it as a which is calling it as a K shell, and n is equals to 2 means L shell, and so on we are going to be have here. Okay. So this is about the principal quantum number, which is associated with the vector atom model. Next, we'll move to the orbital quantum number. So the orbital quantum number, it is representing with the letter L we are going to represent here. So this quantum number defines actually what we call shape of the orbital here. Okay. So this quantum number will gives the shape of the orbital actually. Will gives about the shape of the orbital. So which is occupied by the electron and the orbital angular momentum of the electron. So this quantum number defines the shape of the orbital occupied by the electron and also the orbital angular momentum of the electron. So due to this quantum number, it is also referred to as orbital or what we call angular quantum number we are going to be called. So due to that one, we'll be calling it as a orbital or what we call angular quantum number we are going to be called. So we have the values like integral values are from 0 to n minus 1 we have. Integral values are from 0 to n minus 1 in the case of the orbital angular momentum. So each value from 0 to n minus 1, whatever we have, each value refers to the energy subshell or simply subshell we are going to be called here. Okay. So this the orbital corresponding to L is equals to starting from 0, 1, 2, 3, and so on we are going to be have. So here when L is equals to 0, we call it as a S orbital. We are going to be called when it is 1, we are going to be call it as a P, and then if it is 2, we will be calling it as a D orbital, and F, and so on we are going to be have. So when n is equals to 1, L is equals to 0, suppose if we take, okay, n value is equals to 1 and L is equals to 0 if we are having that there is only one possible orbital which we will be calling it as a S orbital we are going to be called here. Okay. So for n is equals to 2 if you take, so there are two possible values we are going to be have, that is L is equals to 0 as well as the n is equals to 1 we are going to be have. So there are two possible orbitals for this one, like a S comma P orbital we are going to be have. And suppose if you take n is equals to 4 here, after n is equals to 2, n is equals to 4 if you take. So in this case, there are four possible ways. For n is equals to 0, there are four possible ways. So for which what we call L values will be 0, 1, 2, and 3 we are going to be have. That means S orbital, P orbital, as well as a D and F orbital you are going to be have here. So like this, we have for orbital quantum number. And according to the orbital quantum number, the what we call PL value is given by PL value. This is what we call it as a PL value we are going to be called. So the orbital angular momentum, which is given by this one, root of L into L plus 1 into H by 2 pi, it has been given. And one more quantum number which is associated with what we call vector atom model is next one we have is a spin quantum number. So here it is a spin quantum number which we have. This is a spin quantum number, one more which is associated with this vector atom model. So this quantum number has been introduced. This quantum number has been introduced to account for the spin of the electron about their own what we call about their own axis. Okay, so always the spin of the what we call spin of the electron. If you take the magnitude, so the magnitude of the electron always if you take, okay, so magnitude if you take, so the magnitude always it is going to be half. You are going to be half. Either the magnitude may be like a magnitude of the spin will be half. That may be spin may be either a plus half you may be having or minus half you may be having. So these two possible values you are going to be have depending upon the direction of the electron, whether if it is clockwise direction and anti-clockwise direction, you are going to get lead to plus half as well as the minus half respectively you are going to be have. So this is about the spin, and this spin quantum number PS value, which is given by the angular momentum, which is given by PS value is given by root of S into S plus 1 into H by 2 pi we are going to be have. And next quantum number which is associated with the what we call vector quantum number is a total angular momentum quantum number J we are going to be called. We will be calling it as what? Total angular momentum quantum number J we are going to be called. This quantum number this quantum number actually represents the resultant angular momentum of the electron due to both orbital and as well as a spin motion. Okay, so as we said that the electron is having the both we have like a orbital motion as well as the spin motion. Okay, orbital motion as well as the spin motion you have. So due to this both orbital motion of the electron and as well as the spin motion of the electron, So this quantum number has been got, which we call it as an angular momentum quantum number J, we are going to be called. So the numerical values of this vector sum of L plus S, usually we will be expressed as J is equals to this, J is equals to L plus half, we are going to be called. Okay. J is equals to L plus half, we are going to be called here. L plus half, we are going to be called here. So so here the plus sign indicates that we have like a J is equals to L plus plus or minus half also we can get. This is L, actually it is looking like a 1. It is L plus or minus half here. So the plus sign here indicates that the what we call motion is parallel, we are going to be have. Okay. J is equals to L plus half plus or minus half. The plus sign is used here because the S is parallel to L here. S is parallel to L. And when L is anti-parallel to S, otherwise S is anti-parallel to S, then we have the minus sign here. Okay. And for this one, we have a PJ, the total angular momentum of this one. The total angular momentum of this one can be written as a PJ. So which is equals to root of J into J plus 1 H by 2 pi you are going to be have, as we know that H is nothing but what we call uh, Planck's constant we have. Okay. So now 1 minute. Next quantum number which we have is magnetic orbital quantum number. 1 minute. Okay. Right. Next quantum number is orbital quantum number. I'll change it. Right. Next quantum number is magnetic orbital quantum number ML we are going to become. So in the case of this magnetic orbital quantum number ML, when an atom is placed in a strong magnetic field, right? So when an atom is placed in strong magnetic field, the electrons with the same values of principal quantum number M and the orbital quantum number R, L may still differ in their behavior. So when we take this atom into the magnetic field, it is going to be otherwise when the electron is placed in a magnetic field, so they are going to be differ in their behavior. So to account means to know about for this, so we have one more quantum number which we call it as a ML. We are going to be called, which we call it as what? ML. We are going to be called here, which is known as a magnetic orbital quantum number, which is known as magnetic orbital quantum number. So which is known as actually magnetic orbital quantum number, and it has been introduced here. So this is produced by what we call a Zeeman effect and as well as the Stark effect here. So Zeeman effect is nothing but which is reverse. Zeeman effect refers splitting of spectral lines due to the magnetic field. Okay, splitting of spectral lines due to the magnetic field. That means when we kept this atom in a vertical in a magnetic field, it is going to be split the lines, which we call it as a Zeeman effect, right? So while the Stark effect refers to actually what? Splitting of spectral lines due to the electric field. So that is what we have, the Stark effect and Zeeman effect. So according to this rule of space quantization, the orientations of L, the orientations of L and H, if you take, so the orientations of L and H are limited and are determined by the projection of what we call L in the field direction. Okay, in the field direction. So the projection of L in the field direction is known as what? This magnetic orbital quantum number we are going to be called here. Okay, we will be calling the magnetic orbital quantum number we are going to be called here. So if you take you take here, in this figure, actually, projection is here we have, it is not looking properly here, which we call it as a ML. So ML, actually, so ML is nothing but actually L cos theta. So here it has been given. L cos theta it has been given. So because ML has to be an integer and cos theta can be never exceed unit, means cos theta maximum value is unity. Hence, the permitted values of ML are of ML are from plus L to minus L. We have the permitted values of this is plus L to minus L. At unit interval means it is going to be changed like what we call L minus 1 we have, next one will be L minus 2 we have, and so on. It will move to like a 1, then we have a 0, then we have one more minus 1, minus like this if we extend minus 1, we can get minus L minus 2 we can get, and next one we'll get it as a minus L minus 1 we can get. So goes on up to minus L. So in between plus L and minus L. So here it will be, actually it should start from L minus 1, it decreases by unit value, L minus 1, L minus 2, and so on, 1, 0, minus 1, minus L minus 2, minus L minus 1, minus L we are going to be get. So in between the values of ML will be takes place. So here, suppose if we take for L is equals to 0 if you take, because here we have L values can be taken from 0, minus 1 and all this. So for L is equals to 0, actually the ML value also 0. For L is equals to 0, comma, for ML is equals to 0. And for each value of this principal quantum number n, there is only one direction, that is S orbital we have. Only one direction, which is S orbital we are going to be have. So for, suppose if you take L is equals to 1 if you take, so for L is equals to 1, we will get a P orbital we are going to be get. We are going to get P orbital. So here ML value can be take like plus 1, comma 0, comma minus 1. For L is equals to P orbital, ML can be take plus 1, 0, minus 1. So three permitted orientations are possible in this case. So like a plus 1 here, 0, minus 1. Okay. So plus 1 is here, 0, minus 1. Three permitted particle orientation can takes place. And if you go for next, L is equals to 2 if you take. So in this case, ML can take the values starting from plus 2 to minus 2. So plus 2, plus 1, 0, minus 1, minus 2. All these values it can be takes place. So all how many? 1, 2, 3, 4, 5, 5 permitted orientations it can takes place. So this is what we call it as a d orbital we are going to be called. We call it as what? D orbital. Similarly, we'll get for L is equals to 3 F orbital we are going to be get so almost 7 permitted values starting from plus 3 to minus 3. So like plus 3, comma plus 2, comma plus 1, then 0, then we have minus 1, then we have minus 2, minus 3. 1, 2, 3, 4, 5, 6, 7. So 7 permitted values can take. This one we call it as a F orbital we are going to be have. We are going to be have F orbital. So this is about the magnetic orbital quantum number which we have. Next one which we have is magnetic spin quantum number MS we have. So once I erase all these, then we have a okay. So next one we have is a magnetic spin quantum number MS we have here, right? Magnetic quantum number MS. So in the case of the magnetic spin quantum number MS, so just as a vector representing orbital angular momentum processes that it precedes in the presence of magnetic field, so does the vector representing the spin angular momentum. So the numerical value of MS here. So the numerical value of MS is the projection of the spin vector S that is small s, on the field direction. So here ms value in the case of this magnetic spin quantum number is we can write it as a ms we can write. So this ms can be takes the value like a 2s plus 1 we are going to be have. It will be 2s plus 1 you are going to be have. And uh, the values can takes place from minus s to plus s. Minus s to plus s you are going to be have. So we know that it is going to take only minus s to plus s, and we don't have zero here because the electron is does not have any zero spin, but it is having what we call plus half as well as the minus half. It can take only plus half and minus half values. The spin of the electron will be plus half and minus half values. Only two values it can be take here. So now this is about the magnetic spin quantum number. Next quantum number which we have is a magnetic total quantum number mj here we have. Okay. Next one we have is a magnetic total angular momentum quantum number here. Right. So this magnetic total momentum quantum number, which is represented with what we call mj here. So it is represented with the mj, right? So its numerical value is the projection of the total angular momentum vector j. Okay, total angular momentum vector j here. So vector j on the field direction, and j can have the half integral values of mj. It is having the half integral values it is having. So this mj can take the possible values of mj we have is like here it is given. So actually it can take I'll write here. The possible values of mj are minus j, comma, minus j minus 1, and so on. It will extend up to 1, then 0, comma, plus 1. Then we have after this extension up to j minus 1 we have. So here these are the values which we are going to get. Suppose if it is a single electron, it will excludes 0 here, excluding 0 for single electron. So the permitted orientation for this total angular momentum quantum number are 2j plus 1 we have. 2j plus 1 we have. So the permitted orientation of j are 2j plus 1, and hence mj can have only the values of 2j plus 1 values, 2j plus 1 values, which are starting from plus j to minus j, excluding 0. Excluding 0, you are going to be have. So this is what about the principal, sorry, the magnetic total angular momentum quantum number mj we have. So these are some of what we call so these are quantum numbers which are associated with the what we call this vector atom model which we have. Okay. So this is about a vector atom model. So the new two concepts which we have here, it is a like a I'll stop here.